This is Mr. Halsey of 8 Squared, Sufficiently Understood Science, and today we're going to be taking a look at luminosity and HR diagrams. So Hertzsprung-Russell diagrams are a tool that we use to classify stars using their temperature and magnitude, or their brightness. Now it also shows color, since color is related to temperature, if you remember from our EM spectrum review. So there's quite a lot of things that we can learn from an HR diagram just by looking at it. First of all, we can tell it's an object's brightness, okay, and its surface temperature. And our star is right here. So everything on the HR diagram is actually going to be in relation to the sun. So our star is the biggest indicator here. So there's lots of things that we can learn from this. So our star is going to be, as far as brightness, listed as a 1. Okay, and so whenever it comes to brightness, anything above a 1 is going to be brighter than our star. Anything below 1 is going to be dimmer than our star. Also, we can take a look at temperature. And if you remember with EM spectrum, blue or violet is going to be a stronger wavelength, smaller wavelength, and a red is going to be a longer wavelength, so less energy. And so what we can see very easily is that temperatures down here on the red end are a lot cooler, and on the blue end they are much hotter. So we can also, on the HR diagram, get an idea of how big a star is. So these lines that go across here, and please excuse my drawing. Okay, anyway, you get the idea. These are different solar radiuses. So these are a lot. So here's our sun right here. Once again, all the stars along this same line are about the same size as the sun, and as we go up, they get bigger and bigger and bigger. As we go down, they get smaller and smaller and smaller. Now, one thing that we are not going to get to figure out is a star's location. But that's okay. Another thing that an HR diagram is going to tell us is a star's relative age and its life cycle point. All of these main sequence stars right here are going to be in their prime, they're middle aged, okay, and as they age, they'll move up here to the supergiants, and then they make this little zigzag when they get older to the white dwarfs. So main sequence are our youngest to middle aged, and up here we have old and oldest down here with the white dwarfs. So let's relate star color and temperature. So kind of going back to the electromagnetic spectrum. And if we remember visible light, this area right here, that area right there, has different colors dependent on the amount of temperature. So down here on the red end, it's going to be low energy, so lower temperatures. Over here on the blue end, it's going to be higher temperatures. And so Stars that are red, orange, yellow, there are no green stars, sadly to say, at least none that we found so far. But anyway, red, orange, yellow, those are going to be relatively cool stars, whereas blue, indigo, violet are going to be much hotter stars. And so we can see that represented here. Uh, Cooler stars like red stars, about 2500 Kelvin. That's really cool in comparison to other stars that we see. And so their wavelengths are going to show up red. And as temperature increases, and our wavelengths get shorter, we'll start seeing different colors. And so blues and violets are going to be our hottest stars, while reds are going to be the coolest. I mean, we can see a definite difference. We've gone from 2500 Kelvin to 30,000. Very, very easy to see that this is a lot hotter. And so our wavelengths are going to increase. Now, when measuring the brightness of a star, we have to think of its magnitude. So magnitude is measured using negative and positive numbers. And here's where this gets weird, because typically when we think of negative numbers, we think that it is less. And we think of positive, we think more. But when it comes to magnitude, negative numbers mean brighter, and positive numbers are dimmer. Very strange. I don't totally understand. And you can kind of blame this whole confusion really on Hipparchus, who was a Greek astronomer who lived some 2,000 years ago. Kind of very one of those things we just used. And so negative numbers are actually brighter in this case, and positive numbers are dimmer. Kind of based off of like camera aperture kind of stuff. But anyway. So if we were to look at a question that's like this, like which star is brighter, -5 or 5? And in this case, -5 is a brighter star. So we have two types of magnitudes we're going to talk about. First is apparent magnitude. So this is a star's brightness as it appears from Earth. And there are several factors that control apparent magnitude. First of all, how big the star is, how hot the star is, and how far away the star is. So if we look at different things in our solar system, or not in our solar system, but around us, we can look at their apparent magnitude. So if we're looking at these, the sun would have an apparent magnitude of -26.5 because it's the brightest thing in our sky. Okay, and when we're looking at it from Earth, the moon is -12.5. It lights up the night. Venus in the mornings a -4.1. Sirius -1.4. And so here we can see the positive numbers right there. So, and we can see how things being further away, and I want you to remember these numbers, is going to affect this. So Polaris, the North Star, has an apparent magnitude of +2. Things we can see just in our naked eye is a +6. Pluto is a +15, and the Hubble Space Telescope is a +28. So very dim. So this would be very dim. So we're going to look at those again here in just a little bit. But this is as it appears from Earth. So the question is, though, if the sun's negative 26.5, I mean, let's think about this. Is Sirius that much dimmer than the sun? Well, no, because we need to look at absolute magnitude. And so this measures the actual brightness. So two stars with the same absolute magnitude would not be the same apparent magnitude. And that has a lot of different factors. The location of the star is really important. How hot that star is really important. So lots of different factors are going to go into this. So to compare absolute brightness, we use a standard distance of 32.6 light years away from Earth. So let's say we have the sun right here. Our apparent magnitude is negative 26.7. But if we were to view the sun from 32.6 light years away, the magnitude would be a plus 5, so a rather dim star. And so this tells us that even though the sun's super bright in our sky and it's the brightest apparent magnitude, that in reality, our star is a relatively dim star. So we use a standard distance of what would it be like from 32.6 light years away. And so we go back to comparison. So right here we have the sun, which was a negative 26.7. Our distance in light years, not far away at all. But it's so very, very bright to us, apparent. But when we look at its absolute magnitude, it is a 5. Then Alpha Centauri, 4.27 light years away, has an apparent magnitude of 0. It's right in the middle. But its absolute magnitude is 4.4. So this is actually brighter than our sun. Alpha Centauri is brighter than our sun. Same thing with Sirius at 8.7 light years away. Its apparent magnitude of negative 1.4. Well, it's a 1.5 absolute, so it's actually brighter than our sun. Arcturus, negative 0.1. Its absolute magnitude is negative 0.3. So, yeah, it's so we can see that this is the Betelgeuse, 520 light years away, 0.08 apparent magnitude. But if we were 32 light years away from it, its apparent magnitude would be negative 5.5. And so we can see just how much of difference this makes. So remember, apparent magnitude is just how we see it from Earth, but that isn't exactly how it's going to look up close. And so here's our brightness scale utilizing absolute magnitude. The bigger the star, and so we have the Neb and Betelgeuse, Arcturus, and Sirius. And the sun right there. So typically the brighter the star, the bigger that star is going to be. So here we are back at our HR diagram, and we're going to be taking a look at a few different categories. So once again, we see absolute magnitude right there. So how bright that star actually is. And we have a plus 5 here. And that actually be right about where our sun is. So we break the HR diagram into different areas. So right across the middle is what we call main sequence stars. These stars fall somewhere on the main sequence, the main little line here of the HR diagram. And this comprises about 90% of all stars that we can see. 90% of them are going to be in that main sequence. And the sun is a main sequence star. These range anywhere from young stars to middle-aged stars, but they're basically in the prime of their life. Okay, they've not expanded, they are fairly young, or at least evolutionarily wise. You have some stars like down here, these red dwarfs, that will be around for billions and billions of years before they change. So they take a long time to mature, whereas stars up here, like these blue stars or violet stars, they're going to burn out really quickly. So they'll go through their changes really fast. So it really depends on where they are, but relatively evolutionarily wise, they are younger stars to middle-aged stars. So we have our low mass stars down here at the bottom and our high mass stars up here at the top. And so the mass of normal hydrogen burning stars also determine its luminosity and spectral type. And we'll get the spectral type in just a moment. So luminosity right here in solar units, how bright it is, once again. And so up here, we can also tell the lifetime of these stars. Going back to what can we learn from the HR diagram, these, as we go down, so we have a short lifetime here and a long lifetime here. And so as we go down, lifetime increases because high mass stars burn out faster. But this also brings us to the concept of hydrostatic equilibrium. The bigger that star is, the more pressure there's going to be on the core. So core pressure and temperature of a higher mass star needs to be larger to balance the gravity. Remember, we had our diagrams last week where we had the pressure of the core, fusion, pushing outward, and it had to be enough to keep gravity from collapsing in on it. So the higher the core temperatures are going to boost fusion rates, which is going to lead to larger luminosity. So the bigger the star, the more fusion that's needed for it to keep gravity from crushing it, and so the higher the temperature. So in the main sequence, like I said, we have high mass stars, which are high luminosity, short-lived, large radius, they're really big, and they tend to be blue. Then you have low mass stars with low luminosity, long lifetimes, and small radiuses. And they can be yellow or red, but they tend to stay on that side of the spectrum. We can definitely see a big difference in size right here, or not size, but lifetime. 10 to the 7 versus 10 to the 12. Now, that may not seem like a lot, but, if we do. Okay. This is quite a big difference. All right, so let's take a look at this area up here, the giants and the supergiants. So these are going to be older stars. Typically, they have lost a lot of mass and are now, their fusion rates have caused them to expand. So these stars are going to have lower temperatures. Even though their fusion rates are consistent, they've expanded, and so it's kind of like having a heater in a small room and then taking that same heater to a gymnasium. It's going to be able to heat a small room very easily, but a gymnasium, not so much. So stars of lower temperatures and higher absolute magnitudes than main sequence stars. They've gotten bigger, they're easier to see, and they're going to have large radiuses. Down here, we have the white dwarfs. These are stars with really high temperatures at first and lower absolute magnitudes than main sequence stars. And they're going to have small radiuses. And so what you'll notice, though, in our discussions about different star types, we talked about how white dwarfs will eventually just get colder and colder and colder. And we can see a very definite pattern right here where these are just slowly getting colder and colder and colder. And as that happens, as temperature goes down, their luminosity is also going down. So these are actually the youngest white dwarfs up here at the top. And down here at the bottom, we have our oldest white dwarfs. So when we're off the main sequence, our stellar properties depend on both mass and age. For those that have finished fusing hydrogen and helium, they are no longer on the main sequence. They'll be expanding and changing what they're fusing, but all stars do become larger and redder after exhausting their core hydrogen. And so they'll become giants and supergiants. Now, because actually, as we discussed in our previous lab, most stars are not those big high mass stars, at least in the Milky Way. Most stars end up small and white after fusion has ceased as white dwarfs. So it's only those big ones up there at the top that we'll see turn, those high mass stars, that will turn into neutron stars or possibly a black hole. So most stars end up becoming white dwarfs after fusion has ceased. So it kind of makes this weird, like, here's our main sequence. It makes this like zigzag as it ages. Which brings us to spectral classes. So there are several spectral classes that aren't listed here, but they are kind of more of those strange stars like brown dwarfs and stuff like that. But anyway, we have different classes here depending on temperature, because as temperature goes up, we have different colors. So our intrinsic colors of blue, white, yellow, white, orange, and red. You can see the different temperatures here. So as we go up, we can see that our star would be an orangish star. And so it's going to end up being, sorry, excuse me, not orange, yellow white star. So we're actually a G class star because our temperature hovers right around there because we're about 58,000 Kelvin. And so it is part of the main sequence. It's a little less than this, but it's right around there. And so we're considered a G class spectral type. Sometimes called a yellow dwarf star or G dwarf. But anyway, so as we go up, the temperatures rise, causing different colors. And so we have our highest class is an O right there, all the way down to an M. And that's it for luminosity and HR diagrams. Leave any questions you have in the comments below, and we'll try to get to you as soon as we can. But other than that, make sure to like, share, and subscribe, and hit the bell notification to know when we post new tutorials. As always, this has been Mr. Holsey with A Squared Sufficiently Understood Science, and we'll see you next time.